So good morning, everyone. I tried to prepare a sort of relatively self-contained two-set lectures on the very general topic of quantum metrology in open systems, which is of course going to be our first. I put this as we are outside Germany. In case you don't know where is Ulm, which disappointingly seems that many people don't know. So, south of Germany, you're somewhere here more or less, right? This is Baden-Württemberg. And here in the border, this thing here is the Donau, the Danube. Here is Ulm, right? Yes, in the border. In fact, you cross a bridge, it's Neu-Ulm, which is Bavaria already. What you may know is that Einstein was born in Ulm. It was a complete accident. The parents were sort of state employees, and they happened to be in Ulm when he was born, and he was there just a few months as a baby. Nevertheless, you find in the city, well, all sort of remind us that indeed he cannot change his birthplace. And nowadays there is, in September, an Einstein marathon with his aunt. Actually, the University of Ulm would like to be called the Albert Einstein University, which sounds posh in a sense. But the rights of the name are owned by Hebrew University in Jerusalem. So there are negotiations, because you know that everything has a price. So maybe we might. Okay, the plan. I emphasize this some and some in the sense that I'm going to present a rather selective range of topics on some aspects of quantum metrology. There are many, many things that I will leave aside, and obviously it's going to be very biased because I'm going to tell you the things that I particularly have been working on, okay? But I want to emphasize that indeed there is many, especially many recent developments, actually some of them happened here in Nottingham, that I will not discuss. So, in this first lecture, I will try to summarize very, very fundamental topics that, for those of you that specifically work in metrology, I apologize, maybe a little bit boring, but I hope that there is also people in the audience that don't know anything about metrology. Okay, so let's try to set the ground. The general framework is really estimation theory, in the sense that we have the task to be able to provide an estimate for a given parameter that I already select the letter omega, because I will mainly focus on generalized frequency estimations. The thing is that we may have a series of inputs. For the moment, it would even be an entirely classical setup. And then some measurements will be performed that will yield to some probability distribution for the outcomes that is depending on this parameter omega. So then you see that by construction, we are dealing with situations where I cannot access omega directly. This is the typical case where I will measure something else and I will make my way to provide an estimate of omega once I, from this information, typically in statistics, this type of conditional probabilities are called the likelihoods. From these, I should provide a mapping, some function of those that will give me the estimator for omega. You may build many estimators, some will be good, others will be pretty crap. And one important property we will demand is that the estimator should be unbiased, in the sense that given that it itself will be a random variable, by the way it's constructed, the average value should coincide with the actual value of the parameter I'm trying to estimate. Then the question we have is, what is the smallest error we can commit in the estimation of omega? There are many situations where we can actually think about an interferometric setup as characteristic of an estimation problem, in the sense that I can map out in some phase dependence parameters ranging from some atomic transition frequency to many other things that I can introduce simply as a phase shift that results as a difference in the path length when having an interferometer. So I will be biased towards this type of setup where my aim is to determine a frequency estimation. And you can think of actual transition frequencies in atomic systems if you want to have a clear-cut scenario in your mind, or in general, whatever thing that will be scaling cubic Hamiltonian, as we'll see in a second. Okay, so then metrology in general, we would say that we are interested in seeing which fundamental bounds are there constraining how little these error bars can become. Important is that we have to provide some rules for the game, saying what sort of resources you would allow in comparing whether one strategy is more efficient than another. And the resources that I will consider are the total number of prop systems you are allowed to use, trying to keep the notation capital N, and I will put a limit to the total time, capital T, you can be measuring in your laboratory. 3 months, 1 week, but this capital T is fixed. Okay? Then you may know already from your times in the laboratory when you were determining, I guess everybody has done this funny experiment of computing the acceleration due to gravity, counting the oscillations of a pendulum, right? So there you use the error propagation formula, and one result you may have in mind, I will justify it later, from classical statistics is that your uncertainty will decrease as the square root of the number of trials. That you see that even the way I'm speaking is clear that these trials will be independent. I do one, I accumulate data, re-prepare everything again, another set of independent results will come out. Okay? So, it's a very well-known result and a crucial result in classical statistics. I guess the people in the audience that may have been students of Madeline Gita, for instance, if you have proved in detail, we have a result telling us that the smallest this quantity can be is bounded by, okay, this is scaling due to the independent number of repetitions, but the statistical result is that the error in the variance of the estimator is bounded from below by the inverse of what is called the classical Fisher information. It's not difficult to prove it, and in fact I think probably better known that the original proofs are the ones later by Helmström and by Huelga in 82. And I will come back specifically to this function later on. My students are always now demanding to see how the people I'm talking about look like. I think in statistics everybody knows these guys, but I realized that actually I didn't. So in case you have some curiosity, these are Kramer and Rao, which actually Rao is still alive in Penn University. Right. So into our business, we will take as input this result from classical estimation theory. And the point is whether we can change anything as far as fundamental limitations are concerned, if we allow, okay, this is kept as always as fixed resources, but now we have the possibility to use quantum systems to code the value of the parameter. So then we know that this will imply immediately some changes in the game, in the sense that given n particles, that for completion I will set up from now on to be just two-level system qubits. If I'm allowed to prepare them in whatever way is allowed by quantum mechanics, in principle, I would be able to create some correlated state that may have no classical counterpart. And then I will also be able to do measurements as general as quantum mechanics allows again. So I may go beyond simple projective measurements. I may carry out correlated measurements, whatever any general theory I can implement. Okay? One important thing from the rest of the talk is that I will always have in mind this type of a scenario, where you can do everything you want in the preparation, you are also free for the final measurement, but we will impose that the operations by which a dependence on the parameter omega is imprinted on your probe states are such that they act independently on every particle. So I will not allow to have multiple body interactions in here that may yield to other type of scalings. But in this situation, we have a clear-cut result saying that if the dynamics is unitary, so if the evolution of my probe system is ruled by Schrödinger equation, then the fundamental scaling telling me how much I can reduce the value on the uncertainty is now limited by the so-called Heisenberg limit. That is, if I make the ratio of these two, compare the classical statistics result with the Heisenberg limit, I have an improvement that goes as 1 over square root of the number of particles. So let's say in a completely idealized scenario, I would in principle, by means of being able to prepare entangled states of certain type, I would overcome the classical result that I will refer to as the standard quantum limit, or other people call it the shock Young's limit. So let's try to see how this works. Okay, so I have the impression that they are not experimentalists in the audience, but just in case. Very canonical correspondence can be done between this general setup I've been discussing and, for historical reason, I started working on this in the context of Ramsey interferometry. So if you want to move from an abstract setup to a real implementation in physics, the type of discussion I will do applies very nicely to the type of interferometry you do when you try to characterize an atomic frequency. And in particular, this is the type of setup that is part of stabilizing an atomic clock. Okay? So there, our preparation will correspond to some interactions with a laser field to prepare certain superposition states. Then you will have a free precession where some phase is accumulated that will be proportional to the detuning between the atomic transition and external laser driving, right? Then you will do another pi over 2 pulse to mix populations up, and finally do a projective measurement. Okay? So you can see, if you have a look at the type of experimental results people get in quantum optics for the type of population measurements you will do at the end, you see, if you look at the initial part of the curve, that is indeed possible to induce almost full Rabi oscillations. So there is time scales where really the dynamics of the system is pretty much unitary. And if we do a calculation there for the type of resolution we can achieve, then I will use for the moment the very prosaic error propagation formula. Then we see modeling the time evolution in the language of quantum information is equivalent to a conditional phase shift. Nothing happens in the ground state. You get a phase dependence in the excited state, and you have a typical oscillatory signal. Then when you use the error propagation formula, just dividing the variance over the slope of the curve gives you the standard quantum limit at the scaling. So here for its modeling with the inverse of the number of particles. Okay, so then just to keep in mind, in general, I'm dealing with unitary time evolutions with the scheme where the dependence on phi is printed independently on every particle. The resolution, how precise I can be in the estimation of the parameter, is bounded by the standard quantum limit. You would be surprised of how precise things can be done, and the state of the art, okay, this is 2015, I guess, would be more or less the same. The experimentalists are able to characterize the value of an atomic frequency with a quite amazing resolution, 10 to the minus 18. If you have a look on how things have progressed, this is in the specific case of using precision spectroscopy for the stabilization and the characterization of atomic clocks, you see that things that are currently on operation and, well, optical fountain clocks like the ones I showed you below are already on the limit of being imprecise in 1 second per 10 billion years, that you can argue that maybe there is no need for quantum metrology after all. You have even standard quantum limited, you can do a lot. But if you would really like to be able to detect whether indeed there are temporal variations in constants that within a constant, like the fine structure constant or this type of precision measurements, we would still need to go beyond, in case you want some motivation. So there is a way you can think that it would be possible, in fact, to overcome the short noise limit if I alter the rule of the gains, and instead of using n qubits that have been initially prepared in a superposition, like the one I have here, I now apply the transformation u n times on this single qubit alone. Then, if I do as before, the only thing I manage is that this successive application of the transformation u increase linearly the value of the rotated angle in the Bloch sphere. And if I carry out the same determination, just using error propagation for my resolution, I actually notice that I could achieve Heisenberg resolution in this very simple way. However, for practical reasons, you can imagine that this is not going to be easy, in the sense that we would need to keep coherence alive during all the time that this operation is implemented. And effectively, you can achieve the same in a low-dimensional manifold by means of using entanglement states. So if you think about the simplest case, where we have only 2 qubits by means of having, before the implementation of the unitary transformation, an operation that creates a correlated state, in this case, a cat state 1 over square root of 2, 0, 0, plus 1, 1, generalization to n particles is immediate. The final measurement is now, you can do it different ways. You can think of redo the initial preparation, so you disentangle the second fluid and you measure only the first, or you can do a parity check if you want to measure both. Okay, the thing is that when we look at the form of the signal, what is the functional form of the population, which we will move from an oscillations like this in the single qubit case to increase the frequency by a factor of n. Again, using error propagation, we see that this procedure would be able to tabulate the Heisenberg limit. So, putting it pictorially, one possibility to perform quantum resources would be being able to implement this serial performance now in parallel by means of creating a GSX state. So this, if the time evolution is rigorously unitary, would allow a fundamental change in the scaling, going from the standard quantum limit to Heisenberg limit. If we go back to the labs, and especially move from very clear, transparent and real situations in quantum optics, you would see that the oscillations that may start rather vigorously with full population inversion up to 1, you see that very quickly we will start to notice that our systems are not alone in the world. So then the question is, what happens then? What happens if I relax the restriction of the evolution being unitary and now being governed by a general, completely positive and tried special map? So everything as before, I'm allowed to prepare and to measure whatever I want, but now the independent transformations that imprint the dependent on omega on our Probe system are no longer unitary. So the question is, what happens now? What is the fundamental resolution I have in this case? So I will follow a sort of historical approach to tell you what sort of conclusions or what sort of proofs we were obtained, because this is a rather longish story. So we are here now in 97, and the first analysis was to consider a type of decoherence that I will model by the Lindblad equations that you've been discussing with Sabrina. I will assume that the evolution now is such that I have a contribution that is purely unitary, and then have a dissipator that can be written formally in Lindblad form with Krauss operators that you see that they commute with the system Hamiltonian. So populations are preserved, but these things will manage to scramble the faces around. So what happens if we have pure Lindbladian dephasing? Very relevant is that in the moment that you have decoherence, in the moment that the dynamics is not unitary, you have to think that keeping, sorry for having naughty changing n capital and lowercase. Remember that the rules is that the number of particles and the total time you will be measuring are fixed. But you have the freedom of adjusting the duration of your experiment in the most convenient way for you, depending on the type of states you've initially prepared. Okay? So then here you have the task of knowing what sort of noise you are being subjected to. Then it's up to you to see what is the optimal time you can interrogate your system so that to provide the best possible resolution. Okay, so this is what we obtained in 97. Under the type of decoherence I just described, if I perform an optimization to see how long should I wait, you want the interferometric setup in between the two Ramsey pulses to achieve the best possible resolution. If I use uncorrelated particles or maximally entangled state ones, I get that optimally, if I prepare a cat state, now the interrogation should be decreased with respect to the single qubit case by a factor of 1/n. So you can say, fine, you've prepared this maximal entangled state, we'll suffer a lot under this type of incoherence, so don't wait too long. Okay, the point is that when we compare with fixed resources, capital N, what is the best we can do, you see that the resolution we can achieve is actually the same numerical value, and the dependence on the number of particles becomes standard quantum limited. So despite we've prepared GZ states, the resolution they can provide departs, well, has nothing to do with the Heisenberg limit. One can carry out some analytical calculation to see how can I establish a lower bound in the optimal resolution. And at that time, we didn't know how to do it generally in terms of trying to maximize Fisher information. So we used the expression for the classical Fisher information and consider Ramsey type of experiments of probing independently each particle, and then got bound saying that it seems that under that type of defacing, we cannot abandon standard scale dictated by the standard quantum limit, and we may get some constant factors involved. So, analyzing how the improvement in the resolution changes with the number of particles, we saw that, okay, increasing it and using local projective measurements, we will manage to get better precision, and knowing results that I will discuss in a moment from Branston and Hayes, we also perform an optimization in the type of measurement that we will carry out. And seeing that, okay, for a small number of particles, it seems that by means of optimizing the measurement, there could also be a small improvement. But it was really open the solution to the fundamental questions, in the sense that from the theoretical point of view, what we are looking for is an asymptotic result telling us what happens from the point of view of the dependence on n in the limit n tending to infinite. And it was also completely unclear whether these will be saturated at all in the limit of large n, of how fundamental, after all, this result was. Because taking into account that here the prediction is that in the presence of this type of Lindbladian defacing, no matter how little, due to the fact that we have a linear scaling in the decoherence rate and a corresponding decrease by n in the optimal interrogation time, we get that in the moment this form of noise is there, we become standard quantum limit. Was I too fast? Because I wanted to have been that my first lecture, but maybe I did it. That we have room for. What time is it? Half an hour. Okay. Very bad timing. Shouldn't be doing the drone after all. Okay, so then we can go in more detail in this part. Any questions? Maybe a good moment for questions. No, nothing. Okay. So remember, we are in 1997, and we have at our disposal all the tools from classical estimation theory on one side, and a very influential result from '94 that was obtained by Sam Brownstein and Carlton Caves. So from classical statistics, we know that the error in the variance of my estimation not being very precise at all. There are not many mathematicians around, so I'm really identifying the variance in the estimate and not the variance in the parameter itself. Okay, a very important development in the theory was done in '94 when Brownstein and Caves generalized the result of Roundabout to the case of having a quantum setup where now one has the possibility to optimize the final measurement. And the generalization looks like this. Now the resolution is bounded by below by a quantity where I have this new sub-index from the Fisher information, and I have to perform a minimization over all the possible measurement results, sorry, all the possible measurement protocols I can implement. Let me emphasize again that in the moment that the evolution is ruled by a quantum map, then the optimal interrogation time is, as opposed to the unitary case, independent, and is in fact the task of the protocol to identify what is the optimal interrogation time. You may notice that I would argue that by construction, the type of setup we are discussing is suitable to identify the resolution concerning fluctuations around, small fluctuations around a relatively known phase. So the issue of really estimating a parameter when you have no information whatsoever is another business. Okay. So then from the fundamental point of view, the novelty of the work of Brownstein and Caves was linking the issue in classical statistics of estimating a parameter with the problem of optimally discriminating quantum states that are very close. So from the formal point of view, we can think about our metrology protocol as saying, okay, in the moment that I imprint a dependence on omega on my states, effectively what I end up here now having is a generally mixed state, omega dependent, and how well I'm going to be able to determine the value of omega depends on how well a subsequent measurement is able to discriminate raw omega from raw omega plus d omega. So effectively what they do is linking the Fisher information with a definition of a metric in the space of density metric. Okay, so this is a little bit congested, but as we have time, let's go slowly. So let's try to formally say what we want to do. So we have the task of minimizing the variance of the estimator omega, that we assume that is going to be unbiased. So its average will coincide with the actual value of the parameter I try to estimate. Then the result I have from statistical theory is that The Roundabout bound says that this error is bounded from below by the inverse of the classical Fisher information. In particular, we should emphasize that the classical Fisher information is additive, right? It's going to be important later in the sense that I can infer already relevant properties for multi-particle systems from having only single particle channels. Okay, so the classical Fisher information, I also have a way to parameterize it neatly. And the version, the quantum version of the classical, we call it the classical Roundabout bound, is that I'm now allowed to have an expression for the likelihood. I now can perform any QVM beyond. So that would be, let me see, right? This would be a collection of positive operators. The sum of nj and j data should be equal to 1. And I can then re-express, well, this was essentially what Browser and Kate did, was obtaining a closed form for the quantum Fisher information in terms of certain Hermitian operator, which is the symmetric logarithmic derivative that we have here. Relevant, this additive property is still valid in the quantum case. So one can say that, okay, a bound should be very easy to get, taking into account that the only thing we would need to do would be diagonalizing the expression for the quantum Fisher information. But the problem is that this was halted for a long time. We didn't have tools to be able to perform this diagonalization in the limit of large N. And here is a typical situation where the quantum information techniques came to the rescue. So there was, I would say, fundamentally no new results. This is a little bit of a tough comment, but let's say from the point of view of characterizing analytically and in a closed form the best achievable precision for open system evolution, there were no new results from 1997 until we entered in the 2008. I think the work by Imai was one of the most influential, and then the results by the group of Davidovich in 2001, and a series of works by the group of Rafal Benkovic, Dobransky, and also Madame Mika was involved in this Nature Communications in there. But I think I should stop here, or I don't know what sort of stories I will tell you in the second lecture. Okay, so maybe let me summarize. The results we have from Carlton Caves and Sam Brownstein would be that we can build up a quantum version of the quantum Roundabout bound in terms of this quantum Fisher information. The thing is that despite theoretically they would provide us a way to compute the resolution, and actually we use these results in the plot I showed you here. So these optimized measurements are calculated according to the algorithm of Caves and Brownstein, and you see that indeed they allow me to do a little bit better than in case of performance only just projective measurements. But with 7 ions we have to stop. So it was impractical to really try to carry out brute force calculating on what is the optimal measurement which is the one that resolves the symmetrical derivative. Okay? So it was necessary to develop new tools that would allow to establish at least a bound on the value of the quantum fission information. Okay? So those are techniques that we will import now from quantum information. So indeed, quantum metrology is normally argued to be one of the most successful applications of quantum information ideas, and you see that it's true both from the fundamental point of view of importing techniques from the analysis of quantum channels, and also from the point of view of the practical implementation. So I think I will stop here with this expression for the quantum version of the grammar bound, and then we will discuss what happened afterwards. Okay? Right, but take into account that there are many ifs and ifs, okay? So what I said is that, and it's important to clarify that. What I said is that if the evolution is of this form, right? So take into account that here I've already imposed a functional form for the dissipator. So I have pure dephasing, okay? That is acting, and this is something that I didn't emphasize enough. Take into account that by construction, the way I'm implementing the dynamics, you see that in the same way that before I have a unitary operation, now I have a quantum map, so I'm assuming that the errors happen independently. This is crucial for the conclusions we are going to establish. We are assuming an independent error model. In fact, if you have correlated decoherence, you can maintain Heisenberg scaling. So, independent errors, dephasing, this is going to be proven later to be the most damaging type of noise you can have. So noise that commutes with the unitary transformation you are implementing, other ones you cannot correct. So indeed, independent errors, pure Lindbladian dephasing, then here we are. So in the case of product states and GAZ states, you are bound to the same resolution. And there is this prediction that no matter what you prepare, you are standard quantum limited. So for instance, here, when we implement the optimized measurements, we also looked for the optimal states. So in fact, with this type of noise, you could perform metrology with partially entangled states and these optimized measurements that allow you to do better. Okay? But the important thing is that you are fundamentally limited by 1 square root of n. Okay, so these are numerical results, and this is the analytical prediction that at least for local projective measurements, you are a standard quantum limit. So now, let's say from here, it would be open to say, can you actually achieve it? But the conclusion, analytically, would be that for this type of dephasing, you are standard quantum limited. But it's not a proof in the sense that we're going to discuss in the second lecture, where we can prove by means of, optimization of the feature information, the quantum feature information, that for phase covariant noise, so even beyond dephasing, you are a standard quantum. Yes. But the proof has gone stepwise, okay? So let's say that here there were strong indications if you want, right? But then we needed other tools to actually prove it. And maybe, despite I will emphasize it later, take into account that all these limits are asymptotic restrictions. So in the limit of a small number of particles, that's why I also showed you that the result of dynamics is essentially unitary, you can have a resolution that is close to standard quantum, sorry, to asymptotic. So then, just to be sure that we don't anticipate results, keep in mind that for the moment I've been relatively restricted in the sense that I imposed a specific type of noise, that the noise acts independently, and then I have still a big question mark to close. Yes?
Yeah, so in the regime of finite n, you think it still makes sense to consider the quantum Fisher information? Because we're not talking about quantum parallel bound anymore. It's not something that is achievable in the limit of small repetitions. So do you think one should look instead for Bayesian approaches to some recent qualities?
This is another issue indeed, because the meaningful context where the Roundabout bound applies, we know that it's going to only be saturated if it is in the limit of infinitely many repetitions, right? So I don't know, Waffle, for instance, asked that even the number of repetitions may be unrealistic, like large, yeah? So the experimentalists will tell you that the way they compute errors in the lower number of particle domain is with the error propagation formula, and definitely they account for the error bars that they see.
But just to signal to noise ratio.
Yeah, indeed. Okay. So I think one should indeed keep these two domains separate. One thing is what happens in the limit of small number of particles, right? And the other thing is exploring how does that scale up when we move to the domain of n tending to infinite. And there is where we can get fundamental results that tell us, well, something a little bit deep about the structure of the dynamics.
So just sort of relating to the same question then, so there seems there are two different ends being spoken about. So at the beginning you mentioned talking about the central limit result.
Yeah.
When you scale as 1 over n, this is the thing for repeated price.
Yes.
But then you talk about 1 over n squared.
Sorry, take into account, yeah, I'm trying to write always the square, yeah, because this is the way most theory papers are written, yeah, so really characterizing this product. So take into account that then here highs the limit implies 1 over n squared, right?
Yes, but also the repetitions are not taken into account here. So the Heisenberg limit with Fisher makes some sort of a
Yeah, take into account that the discussion of the unitary case is a little bit fussy, right? So I understand what you mean. And in fact, there is a proof that there's due to Raffan templates, I believe, right? Telling you how in the unitary case you wouldn't saturate the Roundabout. So I think, and that's why you see that I avoided, in fact, the derivation of the Heisenberg limit in the unitary case, because it doesn't follow nicely if I then want to analyze this pattern when I have to perform an optimization. So I prefer then to think that as really a corollary of having a type of unitary time evolution not derived within the context of the camera account. I think it's more transparent. No questions from the back of the audience? No?
Another one. So, you anticipated a bit that there have been lots of progresses in optimization of non-official information by using one information techniques like purification and dilation of the channel.
Yeah.
If one is interested in not the non-official information, but the classical official information restricted to a specific type of measurements, because we don't just want to know inclusion. We know very well that like the symmetric logarithmic derivative projection is typically very hard to achieve in experiments. Now, suppose someone says, okay, I am limited to just local projective measurement or local POVMs. Are there techniques that allow one to, again, get very general bounds on what you can achieve with classes of measurements at the output? Or this is something that, in your opinion, is not necessarily there?
So if you use only the classical feature information, we have a chain, right? In the sense that the bound that we achieve with this quantity would be largest in lower bounded by the one of the quantity feature information, right? But we are asking whether there may be cases, and for instance, for deriving the results I told you with runs interferometry, I use the classical feature information, right? So there would be definitely situations where you can get an accurate bound already there. But I don't think that there is any recipe to tell you systematically that you will get it right. Yeah. So
the gap, for instance, we know that if it's just unitary phase estimation without noise, it's sufficient to do global. But in general, whether there is this gap or not, I don't think there are general examples. You need necessarily.
I don't think so, because okay, I think there are results telling you when the resolution cannot be enhanced if for a single particle adding an sealer, a single one. But I'm not aware of anything beyond it, right?
I'm very interested in working with this.
But you should ask maybe Madam in your school.
Or nothing general.
Okay.
We've done some, like on the atom laser, we've done some calculations like this, and you can see the gap between the quantum Fisher information and classical Fisher information of some simple measurement.
Yeah, so you only choose something, we only also did something like this, but could you like optimize over local POVMs? We could.
Yeah, that would be nice, but